Muy buenos días a todos. Gracias por su presencia en este último día del taller Ghost 16. Vamos, como siempre, a dar unos 5 minutitos más para dar oportunidad a los otros invitados que lleguen y enseguida iniciaremos. Muchas gracias por su paciencia. Perfecto, pues estamos listos para iniciar nuestro tercer y último día del taller Go 16. Por supuesto, agradecemos la presencia y el interés de todos ustedes que hacen posible llevar a cabo este taller. Hoy tendremos programado un par de presentaciones a cargo del doctor Scott Lindstrom. La primera es sobre instrumentos ABI, productos nuevos y simulaciones. Posteriormente tendremos un breve receso y luego continuará. Es tan extenso el tema de instrumentación ABI que habrá una continuación con el doctor Lindstrom para concluir. Posteriormente tenemos la comida y para terminar el día hay una visita al Laboratorio Nacional de Observación de la Tierra, el LANOT, que se encuentra aquí en el edificio contiguo a 30 metros saliendo derechito. Pero como es un poco pequeño, vamos a tener que hacer grupos de 20 personas para que todos tengamos la oportunidad de entrar y aproximadamente dura la visita 20 minutos. Y después de eso, pues ya dejamos el día como concluido. Para mañana iniciamos el taller GNC, en donde va a cambiar la dinámica. Ya no va a ser aquí, es importante mencionarlo, va a ser otra vez ya en el de jueves y viernes, serán en las instalaciones del LANOT, aquí enfrente, como les mencionaba, porque es una cuestión ya más de entrenamiento con computadoras y así. Y vamos a tener un simulacro muy interesante el viernes sobre que nos va a dar la NASA, sobre qué hacer en caso de desastres en tema de la comunicación de los organismos e instituciones involucrados bajo presión, porque hay un desastre que atender, cómo tienen que comunicarse, cómo tienen que sacar la información al público y etcétera. Va a ser muy dinámico, muy interesante en un lugar abierto para que cambiemos de paisaje y no estemos encerrados todo el tiempo. También les quiero mencionar algo de mañana que era... sí, mañana tenemos un working lunch, una comida de trabajo en donde estamos comiendo para todos aquellos que son operadores que tienen una antena Geonetcast, porque los colegas de NOAA que están trabajando en este tema de GNC, que es Natalia, Paul y Diego, nos van a dar van a compartir la experiencia de cómo hacer una red con estas estaciones GNC que actualmente las 11 que están en México se utilizan individualmente, pero se le puede sacar mucho más provecho y más jugo a esa información haciendo una red. Entonces nos van a compartir la experiencia de Brasil, nos van a dar algunas ideas y esto pues con la intención de que todos los que tenemos una GNC aquí en México podamos replicar esta experiencia y sacarle más provecho a la información que nos sea útil para todos nosotros. Entonces, sin más preámbulo, antes que el doctor Lindstrom comience su presentación, nos van a dar James McNitt nos va a dar una pequeña introducción sobre un tema que se quedó pendiente. Entonces, muchas gracias.
Okay, gracias. Good morning. Thank you. We want to keep you up to date on schedule changes as they're announced. We received some additional information late yesterday that we'll share with you today in regards to the schedule for GO 17. The product validation schedule is updated as often as we can, and I do distribute this to the GRB user group, which Gabby is an active member. So I'll be sending this out today, and just wanted to brief you on the update. So I'll just read this information. A new product validation schedule was released yesterday for GO 17. It's on the screen here. We have a tentative date of August 27th to hold our review. That's our peer stakeholder product validation review for the GO 17 ABI beta maturity. So on the schedule, you'll see a change from what I showed you earlier in the week on Monday. The change is that we now have a beta review scheduled for August 27th for ABI. If that results in a beta maturity level, okay, thanks. Is that on? Okay. If that results in a beta maturity level validation, then the information that's available on ABI will be transmitted on GRB the day after, and that would be August 28th. So if the review is successful, then whichever products are at the beta maturity level, those will be put on the GRB on the 28th. Okay, let's see what else. So our administrator, Dr. Volz, and the GOZAR program director, Pam, NESDIS website and select press, you'll be able to see that press release that I briefed yesterday, and you can listen to the audio recording. The briefing is about 15 minutes long, followed by another 15 minutes of questions and answers. So some additional information that I didn't announce yesterday. We do plan to make GOES 17 operational. And what I mean by that is that NOAA would assume responsibility for the satellite operations by the end of the calendar year. Any other configurations to the satellite constellation are still under review by several different anomaly resolution teams. And we'll know more about that within the next couple of months. So are there any questions? Okay, thank you. I just wanted to make sure that you had the latest information. Okay, the question was, at what position will it be operational? And that has not been released yet. Also, what has not been released yet as to what the role of the GOES 15 or GOES 14 would be in regards to operating those satellites at and we are not ready to announce at what longitude they would be operating at yet either. But obviously, one of the options is to use our constellation as well as we can. So we're looking at the entire constellation, including GOES 14 and GOES 15 and GOES 17. Okay, thank you.
Where's my...
Are you already up, or do you have to bring it up?
I'm looking for my cursor. Cursor, where are you?
What I do to you here. Looking up.
Oh, there it is.
Okay.
So what Jim means is on August 28th, GOES 17 ABI will be flowing in the GRB, and you'll have a lot more data to save. Buy your disk storage now. Okay, before I start talking about fire, I learned something last night about GLM in my email. The GLM imagery that I showed you from the Weather Service has been processed in a way that's different from what's flowing over the GRB. So the GLM that you see on the GRB has been parallax corrected to a climatological cloud height. The stuff that is flowing to the National Weather Service, so those images that I was showing you, has had the parallax removed because that's what the forecasters wanted. So when you see GLM imagery, I guess the thing to ask yourself is, where did it come from? Because the parallax shift will be different based on whether it's coming from the National Weather Service, from a National Weather Service office, which is what I was showing you, the stuff from Bill Lyon, who was in the National Weather Service in Pueblo, or if it's coming from something like Real Earth, or from a GRB, from your GRB, it'll have a different parallax correction. But it's I guess the good news is the parallax correction is going to be constant depending on the source. So if you're just looking at one source, you will have the same kind of parallax correction. So I hope that was clear. It's confusing to me because there are two parallax corrections, and you have to know what the source of the imagery you're looking at is. But anyway, so the first topic I'm talking about today is fire detection. Kind of timely. You may have heard about the deadly wildfires in Greece in the past couple of days. I don't know if they've been extinguished or not. So wiped out a town, killed more than 60 people, something like that. So gives you pause. Okay, so I'm giving the talk, but the person who's really responsible for this product is someone I work with, Chris Schmidt. So he's been involved in the wildfire automated biomass burning algorithm, or WFABA, for 15 or 20 years now. He inherited from Elaine Prinz, who is the person who started it. She was a NOAA employee. Still might be, I'm not sure. So I hope to do it justice. This is a lot of Chris Schmidt's work, and I'll give you his contact at the end of the talk. So the agenda is shown here, the science behind fire detection. It was touched on a little bit in the questioning yesterday, mostly using the shortwave infrared and the 11.2 microns and some other channels. The history of fire detection, the FDCA is the, I'm blanking on the the acronym right now, Fire Detection and Characterization Algorithm. That's the GOES 16 version of WFABA. So I'll show you a test case over Canada and just where to find it online. And I guess what I can tell you for that last bullet is you can't find it online yet. But you can find the ABI data that goes into it. So at the end of this lesson, I hope you'll understand these things, understand which ABI bands are important for fire detection, understand why those bands work, appreciate how sensitive ABI is to fire sources within a pixel. This is really amazing to me that I'll show you an example. Well, I don't want to give away the whole talk at the beginning. And know where to find fire products online. GOES 16 FDCA has not reached final maturity, so it's still in the provisional maturity. It's undergoing testing and revisions. So you will see, if you look at it, bugs and defects that they're still working on. A lot of that is related to the really nice accuracy of GOES 16. And it's so much easier to detect fires now than with the algorithm that was developed with legacy GOES. So a brief history. This is kind of wordy. I'm not going to read it, but it's here, and you can download this PowerPoint at the end to get a little history on this. But basically, this is something that Elaine Prinz, who was a graduate student at the University of Wisconsin, started this, and then they migrated it to operations. So there are 16 channels. 3.9 is the most sensitive. It was actually designed for fire detection. So it has a very large dynamic range. It detects up to, I believe, 411 Kelvin. So very hot temperatures, it can detect those. But you can see fires sometimes in every single band. And I'm just going to step through for this particular image here. Here we have the bay. This is the fire in Sonoma and Napa counties last October that was pretty damaging to some of the vineyards there. This is the blue band. So this is at night. There's typically not enough energy being emitted in the visible by fires to be detected by ABI. So this is, you really won't see anything in the blue band at night. So you will see stuff during the day, but not at night. Here we have the red band, the 0.64, this is the highest resolution. And again, you're really not seeing any fire signal here. Chris has played with this image to stretch it. So you're really not seeing much of the albedo here, just an albedo of 0.01. So The pattern in here is due to remapping, detector biases, stuff like that. So you can see a signal in here. There's a signal in the noise, but it has nothing to do with fire. If you look at the veggie band, though, you're starting to see energy. So think about the energy being released as a fire is burning. As it gets hotter and hotter and hotter, it gets to shorter and shorter wavelengths. Of course, if it's burning with the energy of the sun, then you'll have something in the visible. Not a lot of fires get to be that hot, thankfully. But we do see in this image some of the hottest fires do have a signal to 0.86. Again, this is all emitted energy because it's nighttime. You can see the same thing in the cirrus channel. So this was a fairly dry air mass, as you might expect from the fire. So you're actually seeing down to the surface, and you're seeing a small signal in the cirrus channel. Again, these are very small values. We're looking at albedos of 0.02 as a maximum. Here we have the snow ice band. So we're getting a really much stronger signal here. So the albedo here is up to 0.602. So you're getting a fair amount of energy. So the one in the circle here is a fairly weak fire, but it's still showing up in the 1.6. It shows up in the 2.2. You'll notice here the difference in resolution. This is 1 kilometer. This is snow ice channel. The 2.2 is 2 kilometer resolution. And then we have the original image that I started with. So that we're just looking at fairly warm. We're not looking. Yes, we're looking at over the entire dynamic range of the 3.9 micron here. So this is the most sensitive ABI channel to fires. Water vapor, of course, there's enough water vapor in the atmosphere here that it's absorbing this energy. So if this were very dry, we might be able to see some of the fires, but nothing. You do have a signal. Here's the 8.4. The signals are still there. 9.6. There's a lot of ozone that's going to be absorbing in the stratosphere, so you don't quite have the same signal. Then we have the clean window, the infrared window. This is the one that's compared to with band 7 in most fire detection algorithms. Then we have the dirty window at 12.3. And you see that those three channels look fairly similar to me. And then we have the CO2. So just to show you that there are 16 channels on ABI. You can see a signal in most of them for almost any hot fire. But the ones that are being used are really just the legacy ones, 3.9 and 11.2. So the fire detection and characterization algorithm produces three different products: fire size, temperature, and radiative power. And there's some masking in there to give you information about the pixels. It's only produced right now for CONUS scans, which is every 5 minutes, and full disk, which is every 15 minutes. So it's not being produced for the mesoscale domains. You can look at the 3.9 in the mesoscale domain if you have a fire that's so hot that's going to be spreading very quickly over 1 minute time scales. But in routine So we have 12 different categories of fires. Processed means that the fire is detected. They have all the information about it. They have the temperature, they have the area, they have the fire radiative power. So it could be something that could be input into a model. So fire radiative power, again, this is a direct measure of intensity, how much energy is being released by that fire. I want to talk a little bit about the Planck function and how this works. So we have wavelength on the bottom here. So we have the 11 microns here. This might be, because of the position of where this is in the Planck function versus 10.3, this might be why they use 11.2, because there's a better discrimination between the two when you have a fire going. So the 3.75, and this is showing 10.8, 11.2 is pretty close to that. The energy being emitted is just so much greater at 3.9 microns. That's the difference here is what's really being used to detect whether a fire is occurring within a pixel. Fires, of course, even with 2-kilometer resolution, are always sub-pixel. Thankfully, you don't want a 2-kilometer size fire burning. So the detection is assuming some kind of distribution like this. And because when that happens, you'll see a brightness temperature difference between those two channels of between 2 and 4 Kelvin. And that's really what's being used to say, okay, ABI is seeing a fire here. So you can, the human eye, if you're comparing the two, will detect the differences as well, depending on how you've enhanced the image, the 3.9 and the 11.2 micron image. So here's an example where we have, on the bottom, we have the 11 micron, and on the top, we have the 4 micron, as we're transitioning between a region where there are fires and where there are not fires. So the 4 minus 11 is showing a lot of information here, but there's this interesting transition zone where we have these big differences between the 4 microns and the 11 microns between the rainforest and the savanna in this transition zone. This is where you start to wonder, well, is this big difference occurring because a fire is occurring? So you have a big difference in the brightness temperature at 3.9 and 11 microns, and you use that to say, to do further investigations on whether or not that there's a fire. So we have an animation here. I hope. Let's see. Well, it is not animating. I don't see it animating. Well, that's unfortunate. What you would see, though, is they're looking at the same scene where we know that there's a fire occurring because this is like apartment building under construction. And it shows up in band 7, but it does not show up in band 14. It's just telling you something about the sensitivity of band 7 to the hot temperatures, the subpixel hot temperatures. But band 14 doesn't show it. So I'm guessing that this next one is not going to animate either. Although they're animated GIFs, so I would think they would. Nope. Well, hopefully if you download this onto your own computer, you will see some animation. Of course, this is a nighttime thing, so nothing is happening in band 2, but it shows up in band 7 and 14, and you also get this processed fire. The nice thing about this is there was knowledge of exactly where it was, because we knew what was burning. So it was just a single apartment building being built in Oakland, California. It was burning, and Ghost 16 could see it. This was when Ghost 16 was in the test position. So it was 89.5 degrees longitude. This is at about 124 degrees longitude. So that's a fairly big that's a fairly big displacement from the subsatellite point, and yet GOES 16 could still pick up this little fire. So it's really a very sensitive instrument, which is kind of exciting. But it also makes it difficult for this automated biomass burning algorithm because it was created with a less sensitive instrument. So there's been some, I would say, growing pains in getting it to function as they want to with GOES 16 versus GOES 13. This was under construction, so I don't think anyone is living there. Okay, here we have an example from, so I live in Madison, which is here. This is Dane, Wisconsin. We have 1 pixel. So this is nominal 2-kilometer resolution at nadir. Up in Wisconsin, it might be 3 to 4 kilometers. So how big do you think this fire is? It's being detected by ABI at 75.2. So we're at 89.5 degrees west, 75.2. This is actually shown here. This was just a gas explosion and then the subsequent fire. And there wasn't much of a signal here because the fire was all contained within these walls. So I think a lot of the energy was going up. It wasn't detectable from the satellite, but was still able to get an area, estimate an area of about 5 acres. I don't know if that's 5 acres. That looks a little bit smaller than 5 acres to me. So as I said, some fire detection might have been blocked by the walls. So it's a very sensitive instrument. You can see very, very small fires, especially if they're fairly intense. Okay, this is probably not going to be animating either. And this is a bummer because this is showing a single house fire. So this is one of the cases where there was a very small detection, very small change in the 3.9 up here. Let's see if I can get it. No. Well, there it is. Very small change in the 3.9. So it's something you can notice with your eye, but it's much less than the diurnal range. So if you watch this over the course of the day, this whole scene got very, very warm because it was daytime, because it was in March. So there was significant warming, but there was a single house fire. So this was the case where the National Weather Service said there's something burning here, and the fire people pulled up to find this house on fire. So it's excellent for for assisting emergency managers to tell them, where are these fires maybe starting, so they can get there a little bit earlier to work on them. So these are things that were, you could qualitatively see them in the 3.9. The algorithm never really caught them because they're such tiny fires. So you have to keep that in mind if you're relying on the algorithm to detect the fires. Sometimes the fires are so small that it hasn't reached that threshold that the algorithm says, okay, there's a fire. But you can typically see things under the 3.9 with the 3.9 microns. Here's another example. This one is not supposed to be animating, so this is over the Yucatan. And I hope you can see here a whole bunch of dark spots. So this is enhanced so that darker is warmer. And the question, of course, is, are all of those dark spots fires? And it's a very challenging region because you have very strong insulation warming up the Earth, and how it's being warmed up is a function of what kind of vegetation is on the surface. So you can get a hot spot forming that might not necessarily be a fire. So this is a much more complicated case. So you can enhance it to see better details. So we have things that look, more likely to be fires because these are the very hottest pixels. And here's what the algorithm showed, that there were indeed processed fires all over the place on this particular day. We're getting close to the region where there's, well, I would call it sun glint if it's invisible, but there's a region where there's extra 3.9 micron reflection coming in. And if you have lakes, for example, or any kind of water body, that can give you a peak in the 3.9. So one of the important things to know is that you know what exactly might be burning. So if you can match these pixels to something that's vegetated and burning versus, you know, an empty lot that is full of sand, that's helpful in determining whether or not these are actually actual fires. So again, algorithm improvement is ongoing. So this is, okay, we'll go back to, this is what the current algorithm shows. This is what an earlier version of the algorithm has shown. Again, they're working on the algorithm to make sure it's better, it better reflects the observations from the higher resolution and the much better precision of the ABI instrument. So GOES sees all different fires. And I guess I should mention, back to those very small fires, typically they don't last very long, and that's one of the reasons you need GOES to determine them. You might be able to see them better with a polar orbiter, but that polar orbiter might be viewing someplace over the ocean when the fire is burning. So you need the temporal abilities of GOES 16 to detect the fires, even though you might not have the great spatial resolution that you get from NOAA 20 or SUMI NPP, which this algorithm is also, a version of this algorithm is also, can also be applied to polar orbiters. Okay, so this is another case of a very quick fire. I'm afraid it's not going to animate, which is unfortunate. So it peaked at 2001 UTC, which is 2 p.m. in the afternoon in Oklahoma in March, and then 20 minutes later it was gone. So again, highlighting that you really need good temporal resolution to detect these. Yeah, not animating, and I don't know why. So let me just tell you that if this were animating, in the middle here you'd see a red processed fire show up and then vanish. And it shows up in band 7 very nicely. So here we have it in band 7. It will not show up in band 14 because, again, band 7 is the band that is very sensitive to the warmer temperatures. And the question was, why did this fire go out? Why was it detected and then not? This is a case where nobody knows what was going on because there was nobody on the scene. So if it was a grass fire, it went out for some reason. I don't know if it ran out of fuel or what was going on. So they do have controlled burns. You typically don't have controlled burns during high fire. This was a red flag day, which is what they call them in Oklahoma when the fire hazard is very high. So you have strong winds and low humidity. So probably not a controlled burn under that circumstance. But somehow this fire started and went out, and the GOES was able to observe it. Now this is another fairly famous fire, the Tubbs fire. I've shown you some imagery from this already. So it's the most destructive wildfire in California history. Killed 22 people, burned 37,000 acres, and a lot of buildings in Santa Rosa were destroyed, including, I don't know if you remember Charles Schultz, the creator of the Peanuts comic strip. It burned down his widow's house. No official statement yet on the cause of the fire. This started very quickly. It was in the middle of the night. The supposition that I have is it was from wires coming together and sparking. There's no indication that it was human caused. Well, arson caused. Yeah. So fortunately, I have each of these individually. So here we have at 9:37 Pacific time. So this is every 5 minutes. And you notice in those 5 minutes in band 7, you do see something changing very quickly. So this fire started very fast. it wasn't detected at 942 by the algorithm, but what is detected at 947. And one of the things that's very interesting about this is just how fast it saturates. So this fire, I think this is 10 minutes after you first saw it, it's showing saturation. So it saturated the pixel, so it grew very fast. It grew very hot very fast. Now, there is an artifact in here that you will sometimes see that's based on the remapping from the ABI grid to the fixed grid. They do a remap, and if you have a very, very hot fire, the remap will introduce cold pixels surrounding that fire. So this white region in this enhancement is cold. So around this very hot pixel, you can think of the remap kind of as a smooth function. It's moving along, and it does have a little negative before it goes up. So there's, I think it goes a minus 2% on either side of the pixel, and a very large number on the pixel to help with the remapping. And if you have a very strong hot signal, that minus 2% will introduce colder temperatures. So this is at 952. After 10 minutes, it has saturated the pixel. Then you'll just see how fast it expands. Oops, how fast it expands in a region. So we have a saturated pixels, very hot fire. So within 20 minutes of becoming apparent, the fire has saturated the sensor. Yep.
Perhaps the animations need the file that it's.
They're animated GIFs, so they should be embedded within the PowerPoint.
So you don't have the files that go. This is supposed to be.
This one is not. This. Let me see something.
Okay. It's animated. Perhaps we can copy it and.
Okay, so what if I do where do I start? Because I started from here, okay. But you can do it from up here to no.
Yeah, well, there's one.
Slideshow. Oops.
We started from the beginning. Yeah.
Well, let's just jump to the first animation. No.
No.
Yeah, they're animated GIFs because typically when I put an animated GIF in a PowerPoint, it just because that's what I was all doing yesterday. So,
oh, wow.
What's changed since yesterday? That's okay. Okay, so I don't think we're going to be able to figure out exactly why the animations are not working. But as I said, if you download these after this conference, they should work on your computer, I hope. And then if not, I'll work with Gabby and we'll get the animations out to you. Okay, where was I? Tubbs Fire, that's right. So it's a good thing Chris put these in each 5 minutes. So again, this is a very quick, and so what this kind of shows you why you really need early detection. This has saturated the fire in 20 minutes. And if you're waiting in the middle of the night for someone to notice that a fire is happening, you might be waiting a long time. If you have an automated system that says, okay, here's a fire, alert the people who need to know about it, you have some lead time here where you can get the firefighters out there or start alerting the people around it to start evacuations a lot earlier. And that's one of the real nice things about first of all, the 5-minute refresh with GHOST 16. So again, this is growth to saturation in 20 minutes. With GHOST 13 or 15, you get every 15 minutes. You've missed a lot of the first part of that. You've potentially missed a lot of the first part of the fire. So here's just an example showing differences between GOES 16 and 15 for this fairly obvious fire. So notice this is a true color image. So this is a red, green, blue composite. And the nice thing about RGBs during the day is smoke is always very apparent because it has a characteristic color. So if you're trying to detect exactly where the smoke plumes are, this kind of visible imagery, combination of visible imagery is very useful because in the infrared channels, it's very hard to detect smoke until it gets very thick. So if you have thin smoke, this looks pretty thin. This probably had very little signal in any of the infrared channels. If you have a pyrocumulus on top and you get a cloud, that shows up very nicely. Or if the smoke gets thick, it shows up very nicely. So, of course, the 3.9 micron signal will penetrate this smoke for a while until it gets too thick. So fire detection should not be impacted too severely by thin smoke. You'll still keep seeing that smoke. So in this case, we have observations from Terra and Aqua using MODIS, from VIIRS on, I guess this was probably SUMI NPP, not NOAA 20, from GOES 15 and from GOES 16. And you'll notice they all have, I would say there's agreement here. Taking into account the different times that the observations are being made, the different spatial resolution, things look fairly similar. Again, note the nice part about GOES 16 is it has great temporal resolution. So here's MODIS at the beginning, Aqua in the middle, and you've kind of missed the big growth and decay of the fire. And then with SUMI NPP, just has one observation here. So you've missed a lot of the early part of the fire. So that's why GOES 16 is kind of vital. Here's another example. Let's see, one was 24th of March. This is 10 days earlier. Comparing GOES 16, which is here, we have similar observations from Terra, Aqua, and VIIRS. GOES 15 never saw this fire. And the question is why? So I won't ask you to volunteer your answer, but it's not size. It's the view. This was on a sloping, so here's GOES 16, here's GOES 15, unfortunately not animating. But the difference is the fire was in the mountains. It was on the wrong side of the mountain for GOES 15 to see it, but it was on the correct side of the mountain for GOES 16 to see it. So that's just one other thing to think about when you're trying to detect a fire. If you're in mountainous terrain, GOES 16 is over here looking on this side of the mountain, GOES 15 over here looking on that side of the mountain. And the fire was on the east side of the mountain. GOES 15 couldn't see it. So this is Oklahoma. Maybe you don't think of Oklahoma as very mountainous, but there are mountains in the eastern part, the Ouachita Mountains that go up into Missouri and Arkansas. Of course, it's very flat, but Mexico is very mountainous. You're kind of fortunate right now when GOES 17 data are flowing. It's at 89.5. That's pretty much over the Yucatan. I think that's where 89.5 is, maybe a little bit to the east. But when you have GOES 16 at 75.2 and GOES 17 at 137, you have to keep that in mind. If you see a fire in one satellite but not in the other. So now we're just going to do a little game here. This should be a little bit more interactive. I don't know if you're familiar with the game Battleship, where you say, G6, where you're shooting people. I'm seeing heads nodding. So you all played this when you were teenagers or younger. So I'm going to show you some gridded coordinates, 0.64, 3.9, 11.2 loops that will follow the frames. I'm guessing they won't animate, but we'll see. This is for, this is not a case in Mexico. When I was looking for cases in Mexico that were similar to this, it was unfortunately a somewhat rainy period, so there are too many clouds. But we're up here in Manitoba and Saskatchewan. So here we have Manitoba is here, Saskatchewan is here. This is the Canada-United States border. And if I were to say, you know, how many fires are you absolutely positive that you see there? 4. Well, I see 1, 2, 3, 4. How about that one? Or this one? This one? See, this is the difficulty with bad temporal resolution. Your eye will really see a change in an image as you go from one time to the next. But if you just throw up one thing, I mean, maybe this is a town. Could be an urban heat island. I don't know if it's Regina, Saskatchewan, Saskatoon. I don't know. I'm not that up on my Saskatchewan towns. But I know there are some of fairly large size. But of course, those wouldn't change that quickly with time. But if we go to the next image at 2015, we'll just toggle between the two of them. And I'll say, how many fires are you more... Do you see a fire that's developing? And I'm looking at F8 down here. Something is changing at that point between these in this 15 minutes. So again, this is Canada does not benefit from being within the CONUS projection for GOES 16. The limit is something around here. So this is only full disk imagery. So you have something over Canada because you have 5-minute imagery all the time in Mexico. So there's 2015, then 30 minutes later, oop, that little pixel that I thought was a fire developing here, gone. So again, a very quick fire shows up and it's gone. But look what's happening. There's something happening here now. So this is a very dynamic day where things are starting and extinguishing very quickly. This fire actually looks to be like one that's pretty intense. So it's growing with time. So 2045 is here, 21Z, 2115. So how many fires do you see now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So they're really pretty much everywhere. They're showing up everywhere. This is one reason why you need, well, this is also a fairly large region. This is the entire province of Manitoba, and here's Saskatchewan. So it's a fairly large region. But if you have responsibility, for example, the southwest part of Manitoba, and you have this kind of information, it's certainly going to help your job because there are not a lot of big cities out here. There are not a lot of people living out here. This could be a fire. I mean, a small fire like this can grow under the wind, the spring winds of Manitoba and Saskatchewan. So you probably have a south wind here at 20 to 25 knots. So this could quickly become quite the conflagration. And if you have a city that's downwind of it, that's something you really need to know about. So you could probably see the smoke plume, but you really do need to know exactly where it is for responders or any kind of people responding to that fire are going to get to. But 2130, that fire's gone. So it looks like the fires are slowly, a lot of these fires are tapering down. Some of them are not. This one is also continuing quite robustly. So 2230, 2245, and 2315. So I hope this is just showing you how dynamic the fire scene is. I'm just going backwards here, and I'll run through it again. So showing you how dynamic the fire scene is, and just with this one band at 3.9 microns, using that, you can determine where you might need to send resources. So that's really for an emergency manager, that's really the takeaway for this. You've got, here in Mexico, you've got 5-minute imagery. You can see how things are changing over 5 minutes, and you will know pretty quickly exactly where resources to fight a fire might be needed. Or, if a fire is burning, but then not showing so much intensity, and if the wind is going to be dying down and maybe more moisture is coming in, that'll show up here too, and you won't need to worry so much about that fire. So this is just a still image at the beginning. So you do see the smoke plumes for the major fires. Some of these small fires never really produce enough smoke to be visible, but they do have a signal. So relying only on the visible imagery, of course, is going to be difficult because it doesn't produce a smoke plume it might not produce a smoke plume with timeliness that you need for the beginning. Here's the 3.9 micron. The 11 micron, some of the hottest fires will show up in the 11 microns. And they do on this case. This big fire here showed up at 11 microns, but the small fires that were down in here were not showing up at 11 microns. And the fire mask captured the big fires. So we have these processed fires, which means it's identified the fire, it's created a fire temperature, a fire radiative power, and a fire area. Then we have a high possibility fire, saturated fire, medium possibility fire. So there are all these different fire legends. So these are all the things that come out of FDCA. I know that in the Weather Service, the National Weather Service, what they only get are the processed fires. So they have a fire temperature in AWIPS, a fire radiative power in AWIPS, and a fire temperature, area, and radiative power. So here's a case where a case in Saskatchewan, and also in mid-May of this year, very dry, windy day, as typical. So it's typically, after it's before the vegetation has started to grow in the spring. So this one was interesting because, unfortunately not animating, but you can see how a wind shift is coming through here, and it changes the characteristics of the fire. So when you see an obvious wind shift coming down, what happens typically is the fire will flare as the wind will change it. And first of all, the wind will ventilate the fire and also change the direction of movement. So it will potentially move it over unburned regions. So the fire detection and characterization algorithm for this did a pretty good job. But again, there is ongoing work with FDCA to make this do a better job. So I'm sorry that the animations didn't work, but here's you've already have my point of contact, and Chris Schmidt's email is there, and he is the algorithm developer. So he primarily works with GOES imagery. There is I would say a parallel effort ongoing for NOAA 20 SUMI NPP polar orbiters that Ivan Cesar at NOAA is the point of contact for that. And I'm happy to take any questions.
Entonces, como siempre, tenemos algunas preguntas aquí de este interesantísimo tema que nos expusieron. Quedamos abiertos. Por acá hay una, gracias.
Bueno, hola, muchas gracias por la presentación de incendios. Aquí arduamente la doctora Lilia Manso trabaja con incendios y yo colaboro un poco con ella. Entonces, tengo una duda acerca de cuando detectan los incendios en el algoritmo, ¿tienen un umbral dinámico durante el día o es fijo para detectarlos entre la banda 7 y la 14?
Do you mean compared to day and night? I mean,
Entre el día y la noche sí son diferentes los umbrales, pero durante el día la doctora Lili ha encontrado que al parecer es dinámico a comparación con MODIS, que sí es fijo el umbral para relevar los incendios más fuertes, ¿no? O que saturan más rápido el píxel. Pero aquí en el caso de GOES, como tenemos ya una imagen multitemporal que es muy buena, ya que se pueden detectar desde el momento que empieza el incendio hasta que termina, ¿es fijo el umbral o es dinámico?
That's a question that Chris could answer that I cannot answer.
Good.
I would hope it would be, because I mean, if I were making this algorithm, I'd be looking at like a footprint around a pixel that I think is hot to compare that. And I think there must be a change in the threshold, because the surface gets so warm, especially at this time of year, that if you're using a fixed threshold, you're going to be detecting fires everywhere.
Okay.
So I don't know the answer for sure. You can email Chris and ask that question, but my guess is based on what I see and how it detects the fires, that yes, there is a threshold that's changing with time during the day. At least I hope so.
Okay.
Because that would make sense to me.
Okay. Gracias.
Gracias. ¿Alguna otra pregunta que tengamos, maestra Gaby?
So you said there's no availability of the FTP or any source of data right now that we can see at the internet or get information of this kind
of products. For the fire products, that's correct. Products. Because it has not reached provisional maturity.
Okay.
And once that happens, I think it flows out over the GRB.
Okay.
So they're still working on minor changes to it, so they're more confident that it's doing what it's supposed to be doing. So for the time being, what you have to rely on is, comparing 3.9 and 11.2, and where there's a big difference, that's where this algorithm is going to be detecting.
Yeah. So it's once it is maturity, reaches maturity, then it will be through the products that we receive as the direct broadcast. No.
Then I think that
we can process through CSPP.
The fire products are not yet in CSPP Geo.
No, they are not.
Right.
Yeah.
So that has to be updated as well.
Yes.
I think they've been waiting to make sure the algorithm is stable before they input it into CSPP Geo. The data that flows, I mean, the interesting thing for me about this is that the weather service offices are getting fire area temperature and radiative power. So it is flowing in one sense, and they're getting that because it has reached provisional maturity. And I think they're waiting, or the algorithm developers are waiting for a bit better or a bit more stable algorithm before it flows out over the GRB. That's my understanding.
But the data, the weather service is only for US.
Yes, but for example, when it does reach the next level of maturity, I know my office mate who works with Real Earth, which I've shown you a couple of times, will be interested in putting it into Real Earth so you can compare, so you can download it. There'll be, and I'm sure other people will do that too. So there will be sources online where you can look at this FDCA product in real time. And then CSPP Geo will also be, when it's, I guess, updated to include this, you'll be able to use that as well. of moisture do you have at the surface, because the water vapor is looking at the mid-troposphere. You could use the veggie, you could use an NDVI derived from the 0.64 and the 0.86 to say, okay, is there green, how green is the vegetation that this fire is moving toward that might slow down the spread, or how brown is it that might increase the spread? So if you have a region, if you have a fire in a region that's moving toward very highly reflective region in 0.86, which is, to me, would say it's very strongly vegetated, and I would expect that the fire would maybe not move through there because the vegetation is healthy, versus where the 0.86 might not have quite so much reflectivity, where you would have dead plants that are ready to burn.
Pero no hay un producto operativo como tal.
From GO16, a satellite-derived product, other than the NDVI, I don't think there is one. There's a total precipitable water. You might be able to infer information from that, but again, that's not going to give you stuff at the surface where the fire is burning. There's a correlation between how much TPW there is and what the surface dew point is potentially, but it's not going to be, I wouldn't be 100% certain.
Okay, we have one more question from this side.
¿El código que tienen utilizando es interno o hay modo de acceder a él en dado caso podríamos?
So the baseline FDCA algorithm, I believe, is freely available. Baseline products, and the fire detection is a baseline product for GO16. There's something called an ATBD, the Algorithm Theoretical Basis Document.
Hold up real quick while you're talking.
And it has all the information on how the products are developed. I would say the difficulty in that is for products that are being updated or modified, I'm not sure how quickly that information gets into the information that's online. So the better thing to do, I think, if you want this, would be to contact Chris Schmidt directly and say, I would like to tweak your code. Is it available? I don't know if he makes it available, but he can say yes or no. So.
Una última pregunta. Hace un rato mencionabas que el sensor tiene una sensibilidad muy bueno, tiene mucha precisión. Y ayer no sé si escucharon que el doctor Magaña comentaba sobre la posibilidad de ver islas de calor. ¿Crees que pudiera haber algo relacionado a esto en zonas, en las ciudades, pues?
I'll try to answer this making a couple statements. You might remember from the ABI talk yesterday, the channel 7, the 3.9, has the most bits. It's a 14-bit channel, so it has 16,384 possible values that it can identify, and those are mostly. It's designed so that those are mostly at the high region. So if you're looking at very cold temperatures, don't use 3.9 because there's just not a lot of. It goes down to like minus 75 Celsius, but it doesn't make it when you're at those cold temperatures. You're looking at a difference between minus 75, maybe minus 73, minus 71, so that you can detect those temperatures, but there's no precision. All the precision is at the higher temperatures. As far as urban heat islands go, I'm not this detector will also be more sensitive to detecting exactly where the hottest part of the urban heat island is going to be. I'm not sure if that is answering your question or not, but so anything that requires differentiation at very warm temperatures, 3.9 is designed to be able to do that. So urban heat island would be one of those things, in addition to fires.
¿Alguna otra pregunta por aquí?
Gracias. Scott, thank you for your presentation. And something I hadn't seen in such a detail is that you shown the image of the energy and the energy emission at 700K, which is about just fire, but it's very high. It is much higher in the 7 band. This is the 3.9 micrometer than at 11 micrometer. It's a lot of energy. And just to mention for the aviation, one of the problems for aviation is smoke from the agricultural fires. In general, say in Mexico, and I know in some Central American countries, maybe somewhere else as well, in some cases the smoke stays there, and we had trouble for aircraft operations, and there are well-known airports which have this problem. And the thing is that the agricultural practices are such that they use fire instead of insecticides in some areas. And the thing is that if you have full moon one day, they will start before the sun comes up. So you don't have visible. But with this one, this seems to be a very useful tool. And this is when the fire gets out of control, when it's very large. I think this is another of the uses that the band 7, the 3.9 micrometer may have, and that's for aviation.
Right, it'll tell you where the fire is starting, but it's not going to. It will not tell you where the smoke plume is spreading.
It is true, but more or less, say there are some agricultural practices. For instance, and in some areas, Mexico, for instance, that's more or less in May. You have the first passage of the sun at the zenith by the middle of May. The second one is this week, actually, that you have it here. It's the maximum of solar energy, but it's in the first passage before the rain begins that they have this, they burn they have the fires in the agricultural fires. And sometimes they are in agreement with the authorities and the fire people and so on. Sometimes if you have the full moon, and when it is not very hot, because in daytime it will be very hot, is the maximum of solar energy, and if you have full moon, they start at night time. But I think this is a good tool. It might be a good tool to detect fires. And we know some airports, for instance, Villahermosa, Mexico, Toncontín in Honduras, and that they have these practices. And this may be has a lot of potential, this tool and these images. Just as a comment.
Yes, I would think so, because you will know the fire is starting early.
Yes, if it's very large.
If it makes smoke and it's near the airport, you'll know that there could be a hazard there, so yes.
Can I add something to that, based on what we were talking about yesterday? I just wanted to add to what Scott said, was that if you couple the fire detection with the modeling capability, then you have a powerful tool. And there's a nowcast capability used in the United States. It's especially useful in California, where they have very strict air pollution rules in regards to agricultural burning. They do a daily blue sky run, and blue sky is a capability that couples fire detection right now using MODIS, but with a dispersion model to determine roughly where the smoke coverage and concentration could be. It's a very rough calculation. And then as you have more information, you can run a more detailed model calculation using the amount of emissions that you think you have, and then put that into a dispersion model. Does that tie into what you were saying?
Sure.
Okay.
Buenos días. Nosotros estamos desarrollando también un algoritmo de puntos de calor basado precisamente en la ayuda que desarrolló Chris Smith preliminar para GOSR, y sí hemos encontrado muchos elementos que nos han permitido identificar esos puntos de calor. Sin embargo, considero que los incendios en México son muy característicos especiales porque se pueden presentar en zonas montañosas o en zonas planas, pero también tenemos zonas desérticas que alcanzan temperaturas muy altas, o en las zonas planas en Yucatán que tienen mucha nubosidad durante todo el año y a veces durante todo el día. Entonces también eso contribuye a necesitar, además de basarnos en la información de la banda 7 y la 14, máscaras de nubes, máscaras de agua y tierra, e inclusive de vegetación. Porque, por ejemplo, muchos puntos se pueden dar relativamente cerca de la planicie costera, donde hay manglares o donde se puede confundir la información del punto de calor para identificar si es incendio agrícola o incendio de vegetación realmente, alguna selva, por ejemplo, ¿no? Y nos gustaría mucho saber, por ejemplo, qué umbrales están manejando en la banda 7 para poder tener nosotros un mejor apoyo para el algoritmo. Tenemos un algoritmo muy preliminar en donde sabemos más o menos los umbrales que debemos de manejar en la banda 7, en la banda 14, o las nubes, o las máscaras que tenemos que identificar. Y si ustedes tienen disponibles resultados preliminares, sería importante poder compartir esta información.
That kind of ties to the first question as well, and I would urge you to talk to Chris about this because he is far more knowledgeable than I am. I know that one of the things they do input is some kind of land use mask, which is a challenge because you have to keep it updated. And if you have a stale, or land sea mask or land water mask is usually pretty more accurate, but the land use mask is the real challenge because that also changes the emissivity of the Earth, which feeds back into what you might expect the difference in 3.9 and 11.2 to be. So again, I'll recommend emailing Chris about that to talk about that. I don't know if he speaks Spanish, though. I'll have to ask him. You might have to, well, Google Translate will change your email from Spanish to English.
¿Alguna otra pregunta tenemos por aquí? No veo ninguna. Entonces, antes de pasar al coffee break, que vamos a hacerlo a las 11:30, regresaríamos aquí nuevamente a las 12 para continuar con la presentación del doctor Lindström. Pero quiero aprovechar para hacer un pequeño comercial por parte de la Agencia Espacial Mexicana. Aprovechando que estamos hablando del tema de incendios forestales, para el mes de noviembre estamos realizando gestiones con la Comisión Nacional Forestal, la CONAFOR, y la Agencia Espacial Francesa, CNES, para hacer un taller exclusivamente para cuestiones de incendios forestales para el mes de noviembre. Entonces, si alguno de ustedes tuviera interés, se acerca conmigo o con Jesús o con Gustavo, que lo tenemos aquí muy ocupado, para darnos sus nombres, su correo electrónico, y nosotros nos pondremos en contacto para invitarlos. Muchas gracias. Entonces, por favor, que disfruten sus café y sus galletas. en el sistema. Cada uno de nosotros vamos a estar en una de las puertas entregando los boletos para la comida. Entonces, whenever you're ready, Scott.
Okay.
Yeah. Muchas gracias.
Thanks for coming back. So the obvious joke is I talked about fires and there was a fire here. And now I'm talking about volcanoes. Fortunately, this fire was not detectable from Ghost 16. And I know you're also thinking, oh, he's talking again. But the one thing I really like to do is talk about satellite imagery. I love water vapor imagery too. So I'm really happy to be able to do this. I thank you for your attention. And on we go. This is my last talk. So you know who I am by now. Matt Gunshore and Scott Bachmeyer are people I work with, and Tim Schmidt is with NOAA, but in my building. So we are a cooperative institute with people from the university, such as me, and people from the federal government. That'd be Tim Schmidt. So the topic today, the last topic I'm going to be talking about is the water vapor channels. Something to tell you about atmospheric moisture. There have been a couple of questions about that. And also, how is volcanic activity detected? So you'll better understand moisture observations from the satellite when you're done with this. Know how sulfuric acid detection is difficult for volcanoes, principally because there's a lot of water vapor there too. And I'm going to talk a little bit more about weighting functions. I touched on them yesterday because I think it's important to understand them to understand where the signal in the ABI water vapor channel is coming from in the vertical. So this, I hope, is a review. There are 3 water vapor channels. As I said, there are 3 infrared water vapor channels. Of course, there's a near-infrared water vapor channel to the 1.38, where there's a lot of water vapor absorption. So these have been nicknamed. 6.19 is the upper-level water vapor. 6.95 is the mid-level water vapor, and not very originally, 7.34 is the low-level water vapor. So the question, of course, is what level is really being referenced here? It varies with moisture. So you've seen this, you saw this yesterday. So here again, we have the three water vapor channels with more water vapor absorption in the 6.19 channel, which is also a little bit broader, and progressively less water vapor absorption in the 6.95 and the 7.34. Notice the 7.34 is a little more narrow as well. Typically, as these channels get broader, you're sampling a bigger depth of the atmosphere. So the 6.19 is sampling a pretty big depth of the atmosphere because it's a broad channel. And when you have a more narrow channel, it's looking at a vertically more compressed region of the atmosphere. So again, something you saw yesterday, the spectral response functions and also what the satellite would be detecting at all these different wavelengths if it was above a US standard atmosphere in clear skies. Of course, if it's cloudy, you're just going to be seeing something that's around here. So this is a clear sky computation. The brightness temperature difference that's solely due to water vapor is shown here. So we've taken the completely dry atmosphere, computed this temperature, and then done the same thing with water vapor and done the subtraction. And again, just to reinforce the notion that each of these channels has some cooling that's due to water vapor. The 10.3 is fairly clean. 9.6 is pretty clean too, but of course there's a lot of ozone absorption there. But there is still some water vapor cooling. And then we see the progressive increase in how much water vapor is affecting the brightness temperature. But the 3 big water vapor channels are here. Same thing, you can do the same thing with SO2. So 7.3, in addition to detecting water vapor, will also detect SO2. And of course, the challenge is to separate them. if you have a volcano that's emitting a lot of SO2, you'll see it in the 7.3. I showed you an animation yesterday of water vapor from Bogslov, I think, in the Aleutian Islands. And it had a nice signal in the 7.3 because of SO2, but also because of water vapor. And then 8.4 also has some SO2 absorption in that wavelength as well. So you can calculate the brightness temperature difference due to SO2, and here, and so we have it really focused in the low-level water vapor band and also in the 8.4 micron. And notice this is really a pretty high concentration, 1,000 Dobson units of SO2. If you had just a minor burp, there wouldn't be much. There wouldn't be much of an effect here at all due to SO2. So what can water vapor tell you? Well, I like water vapor because you can make a guess when you look at the water vapor about the atmospheric circulation. So if I were to ask you, where is the low pressure system where's the cyclonic circulation or the anticyclonic circulation, you can trace out a circulation that's going like this in the water vapor. Of course, it's a lot easier if it's animating. I'm not going to blame the animation here, though, because I know this is a still image. This is not meant to animate. Because if you animate it, well, then it's pretty obvious exactly what the circulation is doing. But you see you can trace out a nice circulation here where we have dry air coming up into Texas. You can do the same thing with the low-level water vapor as well. It shows up a little bit better. Maybe this isn't a great enhancement. But again, at what level, if I were to ask you, what level am I sensing there in the atmosphere? It's hard to tell that because it changes based on both the temperature and the amount of water vapor in the air. And that's what these weighting functions will tell you. And I touched on those a little bit yesterday, and I'll do a little bit more in depth today. So this is a website I showed you yesterday. This is a real-time website where at each of the sounding locations, you would click on it and it would show the real-time clear sky weighting function computed. Of course, if you click on this one, I think that's Aberdeen, South Dakota, it gives you the clear sky weighting function, but of course it's cloudy there. So really all the information in Aberdeen is coming from the cloud top. So again, these are clear sky weighting functions, so make sure you understand if it's clear or not. So, and as I said, it includes Mexican stations. This is something I showed you yesterday. You'll notice this is animating. So these are the same kind of files I was in my other presentation, but these are smaller, so I think it's a memory issue on this particular laptop. That's my guess. So if you have a good laptop, or you have a laptop with better memory than this particular one, you should be able to see the animations from this morning's talks. Okay, this is comparing a fairly moist atmosphere with a fairly dry atmosphere. Again, just reinforcing the idea that if you have a dry atmosphere, you see a lot more information from lower in the atmosphere when you're looking at water vapor channels. And also, as you go from the 6.1 to the 7.3, the peak level that you're looking at is also changing with time. This is what's nice about the water vapor channels on the ABI bands 8, 9, and 10 is you're getting moisture information from different levels in the atmosphere. And that's important to know for example, convective stability. So you can do this for theoretical atmospheres, which is a little bit easier to do. So you can change the band you're looking at, the atmosphere that's being used, the zenith angle, the column water, the moisture, or and the skin temperature. So I'll just show some examples to see how these affect what the brightness temperature that the water vapor is giving you. So here we have a standard tropical atmosphere, 3.9 microns and 6.2 microns. So it's just showing you the weighting functions for the different channels. And you'll notice most of these are window channels. So here's channels, the band 7, the 3.9 micron. It's getting most of its information from down near the surface. Then the water vapor channels are giving you information from the middle of the atmosphere. Then we're back to a window channel, the 8.6. Here we have the 9.6, which is getting information from the surface, but there's also a contribution from the ozone up in the stratosphere. It's hard to differentiate between the two of those in the signal too. So It's called the ozone band. That's the nickname because it's in a region where ozone absorption occurs. It's not necessarily something you can use to detect ozone. So here we have band 13. Again, most of the information from the surface. Band 14 would show the same thing. I don't know why I didn't put an image in there. Band 15 is showing a signal from mostly at the surface, and band 16, you'll notice you're getting some mid-tropospheric or lower tropospheric information in the CO2 channel. So here we have all of them put together. This is for both ABI and AHI, which is the sounder or the imager that's on Himawari 8 and 9, if you're looking at imagery out over the Pacific. And one thing you'll notice here is you have these 3 water vapor channels giving you information in the middle of the troposphere, but all the other channels are mostly giving you information near the surface. So if you wanted to use ABI to tell you what the temperature was in the middle of the troposphere, that's hard to do. There's just not a lot of observations there. Most of the temperature information is coming from the surface. So did you notice? Most ABI channels are window channels. They see the surface. This is different from the GOES 13, 14, 15 sounder that has those CO2 channels around 4.5 and 14.4 microns. If you're looking for temperature information, you get a little bit of it from the water vapor, and you get a little bit of it from the CO2 channels, but that's about it. So if you're interested in the temperature structure in the mid-troposphere and you want to use the ABI, good luck. It's very difficult to get a useful signal. So here are the ones that give you information. Mid-tropospheric information from the water vapor channel, lower tropospheric and stratospheric information in the ozone channel, and some lower tropospheric information in the CO2 channel. Now, what if you warm the surface? So that's what this skin temperature adjustment is. So let's make the surface 10 K warmer. Everything else is the same. How will this change the computed brightness temperature that you're seeing? So this would be a quiz if I were teaching you in a class. So here we have skin temperature adjustment, 0 Kelvin plus 10 Kelvin. And you'll notice the weighting function looks fairly similar. The brightness temperature is almost increased by 10 Kelvin. I think that's, what, 8.8 Kelvin, 8.8 Celsius. Maybe, I don't know, my addition is a little foggy, I guess. But most of the skin temperature change has been picked up by band 7, which is very sensitive to low-level temperature. If you look at band 8, nothing has changed. So you've changed the skin temperature from 0 Kelvin to 10 Kelvin. Brightness temperature is the same, telling you that surface information doesn't go up to is not detected by the water vapor channel. So you can have quite a lot going on at the surface in terms of warming things, but it's not going to give you any signal at the satellite. Same thing with band 10. We still have the same temperature here, same weighting function. Now, if this were a bit drier atmosphere, band 10 might have a better chance of seeing some kind of change in the skin temperature. Band 13, temperature has gone up, the skin temperature has gone up 10 Kelvin, but you'll notice the change in brightness temperature is only 6.9 Celsius, so a little bit less than for band 7. So again, telling you that band 7 is giving you more information at the surface than this window channel. And if I showed you this band 14, so here we have the skin temperature. I don't know what happened here. I must have messed up putting these in here. But band 14 has a similar change. Again, that's why it's useful for fire detection, because when you change the brightness, when you change the skin temperature as you would with a fire, it shows up much more strongly in band 7, and that proportion between band 7 and 14 is what's used to say, okay, there's a fire going on there. Okay, so that's the change in the skin temperature. We can change the zenith angle. So Mexico benefits because the zenith angle, because you're near the subsatellite point, doesn't change too much. But I'm still going to show you what happens when you go from a zenith angle of 0 to 45. Band 7, with a zenith angle of 0, here's that brightness temperature 23.6. There's been a little bit of cooling as you go away from the subsatellite point. So as you scan farther away from the subsatellite point, you're scanning more and more through the colder upper troposphere, and that's going to affect your brightness temperature. And this effect varies by band. Band 12, the ozone channel, has a big effect. So we're zenith angle of 0, brightness temperature of 19. When you have a zenith angle of 45, the brightness temperatures drop down to -6. So the zenith angle changes. So you need to know where you are, because the brightness temperature you're sensing is a function of zenith angle. And here's band 16. The CO2 channel also has a big change. And you can here's a little chart. So we were looking at 45, which is about in here. But we have all the different channels and how for the identical atmosphere, the only thing that's different is the zenith angle, how it's scanning through the atmosphere. And we have the cooling that's going to be apparent. So for water vapor information, where's the level? For a dry atmosphere, it's from lower in the atmosphere. If you're far from the subsatellite point, the information comes from higher in the atmosphere. If it's a longer wavelength, that is 7.3 versus 6.19, it's from lower in the atmosphere. So when is the water vapor channel can be a window channel if you have a very dry atmosphere. So here's an example of that water vapor channel I showed you earlier, and we're looking at Corpus Christi here. That's where the cursor is on, and it has the brightness temperatures for both the 6.19 and the 7.34. So there's a readout coming from AWIPS. AWIPS tells you the brightness temperature. And the question is, what level is that at? Now you could just look at numerical model data and say, okay, I know from the GFS this morning, or whatever model you use, that -31.C is at 416 millibars or something. But you can also use these weighting functions. So here is the weighting function from that day and time at Corpus Christi. And we have again, these are clear sky observations. The upper level water vapor has most of the information, or the peak in the information is coming from around 329 millibars. And here we have a brightness temperature. Mid-levels coming from 340, peaking at 344. Low levels peaking at 442. So if this was a case where, as it says, as dry air moves over Corpus Christi, the peaks in the water vapor functions should drop because there's less water vapor absorption, so the satellite should be able to see farther down into the atmosphere. So there's the total precipitable water, 1.34 inches on this particular day. Then here we have another so 24 hours later, it's gotten a little more moist, 1.41, but you'll notice all the weighting function peaks have dropped. So I just told you that if there's more moisture, they should go up, but that has not happened. But if you look at the sounding, which is in here, in this particular sounding, we have a lot of there's some cirrus at the top. So there's a lot of moisture at the top of this sounding, and that's what's helping to have these weighting functions peak a little bit higher. And 24 hours later, the upper levels have dried out a lot. So you're seeing more information from lower down in the atmosphere. So you have more moisture as measured by total precipitable water, but the peaks have dropped because the upper troposphere is drier. So I hope I'm getting across the point that understanding exactly where these peaks are going to be is kind of complicated. It's not just the moisture, but it's where the moisture is located in the vertical too. Okay, so not a lot of moisture about the boundary layer, which is where all the moisture is, but one of the level 2 products coming from GOES 16 is total precipitable water. And that's how you can tell where moisture is in the atmosphere or where there is dryness. So here we have an image of water vapor. This is the low-level water vapor, and my question for you would be, where are the moisture gradients? And of course, it's a trick question. By now, I hope you think you're saying, well, I don't know because I don't know anything about the surface moisture distribution based on this particular image. But the total precipitable water is shown here. So we have a nice moisture gradient here, where we're going from something around more than an inch to something around a half an inch. And again, if you look at the water vapor in that region, you really don't see any gradients. So the total precipitable water level 2 product is an important thing to use so you understand exactly where the deep moisture is in the atmosphere. So I do have the water vapor. Okay, total precipitable water, this is obviously a clear sky only product. So where we have clouds, I've put in the water vapor. And just underlying the total precipitable water with the water vapor so you can see some of the features in the water vapor. So I made it a grayscale though, so the color scales between the two don't start to blow your mind. Okay, changing topics a little bit to volcanoes. As I say, 8.4 microns and 7.3 are both sensitive to SO2, so they can be used to detect volcanic emissions. But there's a lot of difficulty in there. This is a graph, a fairly complicated graph, comparing the absorption of upwelling radiation at 8.5 microns versus around 11 microns. So energy that's coming up from up below is not, if you have some kind of cirrus cloud or water cloud, it penetrates it fairly quickly. Whereas around 11 microns, there's more absorption. So the energy from underneath is being intercepted at 11 microns, so it'll be a colder temperature, it's absorbed and re-emitted, versus at 8.5 microns where it passes through mostly unadulterated by the clouds. So the brightness temperature with cirrus clouds will be warmer at 8.5 than it will be at 11 microns. And that complicates how you can infer what's going on with a volcano if the volcano is producing a thin cirrus or it's occurring underneath a thin cirrus. If there's, for example, jet stream cirrus above it. So here's some examples. This is GOES 16 imagery with Popo Kappa. I can only say Popo. So we have in the blue band, you see a little bit of the ash plume is showing up fairly nicely. Popo Kappa Catapedal. I have to see it written down because then I know where the P and the T are. This is band 4, the 0.47 and the 0.64. And in this particular case, the cloud shows up mostly the same. You do notice between 0.64 and 0.47, typically 0.47 has a little hazier look to it because there's more scattering at that wavelength. So the atmosphere doesn't quite look, it's harder to distinguish between some land features. Some of that is the difference in resolution because 0.64 is half kilometer and 0.47 is 1 kilometer. But some is also due to the physics of scattering in the atmosphere. Here we have the 8.4 micron, and it does show up fairly nicely in here, but it's also showing up nicely in the 11.2 micron, very similar look to it, which tells me that maybe some of this, maybe a lot of this cooling, I mean, there's part of it right there, doesn't really show up in the 11.2, so I'm thinking maybe that's an SO2 plume, but there's SO2 and water vapor being emitted by this volcano, so it's very difficult to interpret it correctly. For me, at least. There are probably experts who know how to do this. Here's another example with, it's the one in Guatemala that went off, yeah, in early February. So here we have the 8.4, here we have the 11.2. They look very similar. And if you take the difference field, there are regions in here. But again, this is probably more controlled by thin ice clouds and not by SO2. So I question whether there's a lot of SO2 being emitted from this volcano. But I don't know because I'm not a volcanic expert. This is one that's supposed to be animating. This is a huge file. And I think it's too big, but it shows you how the volcanic activity is visible in all of these bands if it's impressive enough. And this was a pretty impressive eruption on June 3rd down in Guatemala. There is a website that is if you are interested in volcanic monitoring, this is a website put together by Mike Pavlonis and some of his colleagues in NOAA. Mike Pavlonis also works in Wisconsin. And he is the person who has developed the volcanic detection algorithm for both GOES 16 and for the polar orbiter. So he's a better, I trust his interpretive skills of volcanic eruptions way more than mine. And he has this over here. So if you go to this particular website, volcano.ssc.wis.edu, there's a link there for satellite imagery. And then you click on that and you can choose the sector. So there's a sector over Mexico. There's a sector over Kilauea. There are sectors over many common volcanic eruption zones or over commonly erupting volcanoes. So you can choose an instrument, a satellite, so you choose GOES 16 and ABI, for example, image types, and then an end time and a date range. So you choose all of those things, and it'll put out an animation or something that looks like this, where we have a false color imagery, where it's looking at the 12 minus 11, 11 minus 8.5, and 11 micron. For GOES 16, that's actually 12.2, 11.3, 11.2. So they kind of truncate them. But there are similar channels on VIIRS, which is why that's used. So after you choose that, you get imagery that you can interpret, and this is a false color imagery. So when there's something happening, you get a very unusual color in there. So if you're used to looking at the false color imagery, the volcanic eruption will pop right out at you. So how do you observe it with GOES 16? Well, here's a animation this is Fuego over Guatemala. So we have ash and dust cloud height from that particular eruption, and it shows the observations from GOES 16. And here we have the estimates from the satellite of the ash and dust height. And in the background is the brightness temperature from 11 microns, 11.2 microns. So it's a way to just get animations or imagery when a volcano is erupting. Now, how do you know when the volcano is erupting? You can also sign up at this website for alerts that will be sent right to you by phone or by email. I will say that the VAC people at the volcanic something activity centers are monitoring the satellite imagery, and they probably know more than anybody because that's their job. So I would trust an alert from a VAC versus just something that a person looking at this imagery would look at. So accurate interpretation of satellite respective volcanic activity, that's a benefit of that, because I would add, if we weren't talking about the benefits, I would just say it's very difficult for this first point. But it's not difficult for the experts who are using this site at the VAC. And that's all I have today. I'm standing by waiting for the volcano to erupt in the middle of the room. So I'll entertain any questions. Except I don't have I turned in so wait 1 minute. Oh. When I thought we were moving, I turned in thanks.
¿Tenemos alguna pregunta por aquí? ¿Preguntas? Bueno, entonces, pues un aplauso, por favor, para el doctor. Ahora ya tenemos la parte de la comida, en donde vamos a repartir los boletos en cada una de las salidas. Una cuestión más. De regreso ya no hay más presentaciones. La única parte que falta es la visita al ANOT. Yo no sé si todos están interesados. ¿Quiénes? ¿Podrían levantar la mano para saber los grupos bien arriba? Ok, si somos más de 20, ¿no? Ok, entonces van a ser 2 grupos, porque no pueden entrar más de 20 personas. y dura aproximadamente 20 minutos la visita. Entonces tenemos primero un grupo en donde, digo, por una cortesía de nuestros visitantes extranjeros, van a estar en el primer bloque y el resto pues ya entra 20 minutos después. Entonces yo creo que para cuestiones de logística mejor nos vemos aquí y de aquí ya armamos los grupos y nos vamos al laboratorio Lanot que está aquí a 2 minutos caminando. Pues buen provecho y muchas gracias. Quien se quede sin boleto se acerca conmigo por favor para que resolvamos el tema.